All right, let's talk about inductive and deductive reasoning. Inductive and deductive reasoning are both important tools to mathematics. So let's talk about those, right? Inductive reasoning is the process of drawing a general conclusion by observing a pattern in specific instances. This conclusion is called a conjecture, or sometimes we call it a hypothesis, but I'm going to refer to it as conjecture. In deductive reasoning, we use accepted facts and general principles to arrive at a specific conclusion. So in some sense, they're sort of opposites of one another, right? With inductive reasoning, you're going from general to specific. It's like you're saying, oh, we've observed this thing to have happened over and over and over again, so we think it's always going to happen, right? So an example of inductive reasoning would be, every organism we've ever studied is made of cells. Therefore, all organisms are made of cells, right? That's inductive reasoning. Another example of inductive reasoning would be like, the sun has risen every day of my life. Therefore, the sun will rise tomorrow, right? That's inductive reasoning. Deductive reasoning, on the other hand, goes from the general to the specific, in the sense that you start with facts that are already known or already accepted, and then you use them together to arrive at other conclusions. So for example, all organisms are made of cells. Humans are organisms, therefore humans are made of cells. That's deductive reasoning. So again, to give you the sun example, right? Inductive reasoning was, well, the sun has risen every day of my life, therefore the sun will rise tomorrow. Deductive reasoning would be for you to actually like sit down and figure out how gravity works and figure out, why the sun or why the earth revolves around the sun and stuff, and then use all of that reasoning to deduce the fact that the sun will in fact rise tomorrow, right? So that's the difference between inductive and deductive reasoning. In math, we use both kinds of reasoning, but typically we use them for different purposes. So in math, we often use inductive reasoning to find conjectures, but then once we have a conjecture, we try to prove it using deductive reasoning. So I'll give you an example of this. And again, we're sort of on this quest to understand, what is mathematics, right? And I think this sort of thing will help you to understand almost more than anything else we'll talk about in this class. This sort of thing, this sentence right here will help you to understand like what it is that mathematicians do, right? So they typically use some inductive reasoning to find a conjecture, right? To find something that they think is true. And then once they have a conjecture, they try to prove it using deduction. So for example, you may recall that if n is even, remember the even numbers are 2, 4, 6, 8, 10, right? So if n is even, then it's a multiple of 2. So you should be able to rewrite it as 2 times some other whole number, k, right? So if n is even, we can rewrite it as n equals 2k for some whole number k. On the other hand, if n is odd, the odd numbers would be like 1, 3, 5, 7, 9, right? So if n is odd, then it can be written as n equals 2k plus 1, right? So you take an even number, you add 1 to it, and you'll get an odd number, right? So if you take, 6, you add 1, you get 7. Sure enough, 7 is odd, right? Okay. A number's parity is its designation as even or odd. Okay, so far, these are just definitions, right? Now, part A says, use inductive reasoning to make a conjecture about the parity of the sum of 2 even numbers. Okay, so the sum of 2 even numbers. Sum means add. So we're going to add up 2 even numbers, and let's see. So I could start with something small. I could start with like 2 plus 4, right? 2 plus 4 equals 6, right? Okay, so let's try something a little bigger. Let's try like 28 plus 72. Right? So what's 28 plus 72? 28 plus 72 is 100. Okay. Should we do this again? Let's do this for a big number. Let's do like 32,500 576 plus 54,004. We'll say, I don't know, 32,576 plus 54,004. We get 86,580. Okay, so we could keep looking at examples like this. We could look at example after example after example, right? And maybe there are lots of different conjectures that you could come up with. But here's one conjecture that we could make. We could say, well, it seems like when I add two even numbers, I get an even number, right? 6 is even, right? We can rewrite 6 as 3 times 2, or 2 times 3, right? So that means 6 is even. When I add 28 plus 72, those are both even numbers, and I get 100, which is also even. I can rewrite it as 2 times 50. And when I add 32,576 plus 54,004, I get 86,580, and that's also an even number. Let me see what it would have to be. We can rewrite it as 2 times 43,290. Okay, so it seems like every time I add two even numbers, I get an even number back, and so that's the conjecture that I'm going to make, right? So my conjecture, and by the way, I don't expect this to be earth-shattering. I bet you knew prior to this class that the sum of two even numbers was an even number, right? But anyway, let's write this down. So the conjecture is that the sum of two even numbers is even. Okay. So that's inductive reasoning, right? We're saying, well, we looked at a bunch of examples, and based on our examples, we always got an even number. So we're going to go ahead and conjecture that the sum of two even numbers is always an even number, right? So that's inductive reasoning. Part B says, use inductive reasoning to make a conjecture about the parity of the sum of two odd numbers. Okay. So now we have to add odd numbers. Let's do, again, we'll start with something small. Maybe we can do like 5 plus 7. Okay, so 5 plus 7 equals 12. So right off the bat, it's like based on our previous thing, when we added two even numbers, we got an even number. So you might expect that when you add two odd numbers, you get an odd number. But right off the bat, we see that that's not true, right? When we add two odd numbers, it looks like we got an even number. Well, let's try this with bigger odd numbers. Let's do like 353 plus 511. Okay, so 353 plus 511 is 864. Okay, so another even number, right? Well, let's try another one. Let's do 2,571 plus 2,571, right? They're both even numbers, or sorry, both odd numbers, so this still works. 2571 plus 2571 is 5,142. Okay, so another even number, right? So, okay, so it seems like the sum of two odd numbers is also an even number, right? So that's the conjecture we'll make here. The sum of two odd numbers is even. Okay, so that's interesting. So now so inductive reasoning on both of those examples. But now part C says, use deductive reasoning to prove the conjectures that you made in parts A and B. Okay? So typically this is a little bit more challenging, but let's see if we can do it. And all we have to go off of are the definitions that we had in the statement of the problem, right? So if it's even, we can rewrite it as 2 times k. If it's odd, we can rewrite it as 2 times k plus 1. So let's see. So proof of part A. So we'll say proof of A. So we're going to add two even numbers. So let's give them a name. And this has to be done in general. Okay, so we can't use any specific examples. we have to do this generally. So we'll say let x and y be even. Okay, if that's the case, then x equals 2 times k, I'm going to call it k1, and y equals 2 times k2, right? So I'm calling them k1 and k2 to distinguish between them because they're not necessarily the same numbers, but it must be the case, since x and y are even, that we can rewrite both of them as 2 times something else, right? For whole numbers k1 and k2. Okay, so then we can say, well, what's x plus y? So then x plus y would be 2 times k1 plus 2 times k2, right? Because x is just 2k1 and y is just 2k2. So I'm replacing x with 2k1 and y with 2k2. Now, you may recall the distributive property. Or if you're using distribution in reverse, then we sometimes call it factoring, right? And here I can factor out a 2. So I can call this 2 times k1 plus k2. And now notice, k1 plus k2, whatever numbers those are, when you add them up, they're still going to be whole numbers. And so x plus y is 2 times a whole number, right? So this is just a whole number. So we've shown that the sum of x plus y is 2 times a whole number. That means it's even, right? So therefore, x plus y is even. And that concludes the proof of that conjecture, right? So that's deduction. At first glance, you may say, well, I've never done proofs like this before, so I've never used deductive reasoning. And that's not quite right. I'll show you later on in this section that you're actually really familiar with deduction. You just maybe have never seen it quite in this way, but that's all right. Let's see if we can prove part B. Maybe I should use a pencil because I might make a mistake that I need to erase, but we'll see. Okay, well, this time let's let x and y be odd. Okay, and then we'll do the same thing, right? If x and y are odd, then x equals 2 times k1 plus 1, and y equals 2 times k2 plus 1 for some whole numbers k1 and k2. All right. And then when we add them, we would get 2k1 plus 1 plus 2k2 plus 1. Well, we can add those up, right? The parentheses here aren't really doing anything. I just put parentheses around them to emphasize that this is x, right? And this is y. But when we add these things together now, it looks like we've got, well, k1 and k2 are not the same variable, so we can't combine them. We just have to call it 2k1 plus 2k2. But 1 plus 1, we can combine those. 1 plus 1 is just 2. Okay. Well, notice that we can factor out a 2, right? So this equals 2 times k1 plus k2 plus 1. And there you go, right? So k1 plus k2 plus 1 is just going to be a whole number. So we've shown that x plus y is 2 times a whole number. Right? So if x plus y is 2 times a whole number, well, then that must mean x plus y is even. Okay? And that concludes that proof. So there you go, right? So we've got inductive reasoning here, where you're basically just looking at examples and you're trying to come up with like a conclusion based on just looking at a bunch of examples. And then you have deduction, which is more like a proof. It's like you just suppose that these are any two random numbers, and you just prove in general that it must be the case that if they're both even, their sum is even, or that if they're both odd, their sum is odd. Their sum is even. If you have an even number plus an odd number, then you get an odd number, right? But we're not going to look at that. Okay, let's practice with induction a little bit more. So this one says, for the numbers 72, 491, 963, 19,865, 45,307, and 7,538. I don't think I need this extra one. It says, use a calculator to determine if the number is divisible by 9. Then add the digits of each number. Use inductive reasoning to make a conjecture about your findings. Okay. So for 72, that we don't even need a calculator for. 72 is just 9 times 8, right? So we know that 72 is divisible by 9. Maybe I'll make this a chart. So I'll put the number here, and then I'll ask, is it divisible by 9? And then we're also supposed to add the digits of each number. So I'll say sum of digits. Okay, so for 72, is it divisible by 9? Yes. What are the sum of its digits? 7 plus 2? 7 plus 2 equals 9. Okay, next number, 491. Is it divisible by 9? Well, I'm going to use my calculator for this one. 491 divided by 9 is not a whole number, so the answer is no. Okay, when I plug it into my calculator, this is what I get. So I know that 491 is not divisible by 9. What's the sum of its digits? 4 plus 9 plus 1 is 14. Okay, 963. So 963 divided by 9 is 107, right? It's exactly 107. So is 963 divisible by 9? The answer is yes. What's the sum of its digits? 9 plus 6 plus 3 would be 18. Okay. 19,865. Let's see if that's divisible by 9. 865 divided by 9. No. What's the sum of its digits? 1 plus 9 plus 8 plus 6 plus 5 is 29. Okay, 45,000. So just a couple more. 45,307. Okay, that's also not divisible by 9. And 4 plus 5 plus 3 plus 0 plus 7 is 19. Okay, and then 7,538 divided by 9. That's also not a whole number, so we'll say no. And 7 plus 5 plus 3 plus 8 is 23. Okay, so we've seen a couple examples of numbers that were divisible. Maybe we'll do 403. Maybe I shouldn't have scratched it off. I mean, let's throw 403 into the mix. Why not? 403 divided by 9. Oh, that's also not. Never mind. I was looking for another one. Let's maybe think of another example of something that is divisible by 9. So something like, let's see. If I do 9 times 57, I get 513. So I already know. So I'm kind of rigging this. So I know that 513 is divisible by 9. Yes. 5 plus 1 plus 3 is 9. Okay. All right. Very good. So it says, use inductive reasoning to make a conjecture about your findings. So conjecture. Well, these are the numbers that were divisible by 9. And notice that the sum of their digits, 9, 18, and 9, those are all divisible by 9, right? They're all multiples of 9. 9 times 1, 9 times 2, 9 times 1. So, meanwhile, if you look at the ones that are not divisible by 9, these numbers are not multiples of 9, right? 14 is not a multiple of 9, 29 is not a multiple of 9. So the conjecture, so one conjecture that we could make is that if a number is divisible by 9, then the sum of its digits is also divisible by 9. Okay, and based on the examples that we've seen, that would be a conjecture we would make, right? Now, this conjecture happens to be true, right? And it can be proven deductively, but we don't have time to get into it, so we're not going to do the proof. However, as you can see, inductive reasoning is very useful. It helps us to sort of get our bearings, right, and make sense of the world around us. It helps us to discover things that we think might be true, and then we use deductive reasoning later on in order to verify that those things are true, or verify if they're true. Right? Now, in addition to being useful for helping us find conjectures to prove, inductive reasoning is also helpful as a problem-solving strategy, and we actually saw this in the previous lecture. We saw some examples of this, but here's another one. Let me give you another example where you can use kind of some inductive reasoning to help you solve a problem. So this one says, suppose that Sharifa is going to visit the branch offices of her medical supply company in Boston, New York, Cincinnati, Miami, Detroit, Portland, Los Angeles, Houston, and Kansas City. She can visit these branches in any order she wants. How many different ways are there for her to order her trip? And then I'm giving us a little hint here that says try simpler examples first and then use inductive reasoning. Okay. Okay. So simpler examples. It looks like we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 cities. Thinking of all the different ways to put 9 things in order, that's a pretty daunting task. So let's start with something smaller. Let's start with, if we start with one thing. So let's do it. Let me make a little table. So we'll say number of things and number of orders, right? Number of ways to order that number of things. So if you only have one thing, there's only one way to put it in order, right? What if you have 2 things? How many ways are there to put 2 things in order? So let's say, in this case, let's say you have Boston and New York. Just those 2 cities. How many ways can she go? Well, she can go to Boston first and then New York, or she can go to New York first and then Boston. So there are 2 ways to do that. What if you have 3 things? So what if you have, in this case, 3 cities, Boston, New York, and Cincinnati? Well, let's see. You could have Boston, New York, and Cincinnati, or you could have Boston, Cincinnati, and New York, or you could have New York, Boston, Cincinnati, and BC, or you could have New York, Cincinnati, Boston. Okay, so we've done 2 where B comes first. We've done 2 where N comes first. Let's do some where C comes first. So you could have Cincinnati, Boston, and New York. Or you could have Cincinnati, New York, and Boston. Okay, and then I think that exhausts all of the possibilities. So there are 6 ways. Okay, So if you were thinking it would be 1, 1, 2, 2, 3, 3, well, this kind of messes it up, right? Let's see about 4. Let's see about 4. So again, we'll use cities. Boston, New York, Cincinnati, Miami. Ooh, so Boston, New York, Cincinnati, Miami. Okay, I'm going to cheat a little bit. I'm going to say, well, if we assume that Boston comes first, we already know that there are 6 ways to order these 3 letters, right? We just did it a second ago. So if we know that Boston comes first, then there are 6 ways. So maybe I'll say this. If B is first, then there are 6 ways to order the remaining 3 letters. What about if New York comes first? Well, then you would have to reorder B, C, and N. So there are still 3 letters there. There are going to be 6 ways to do that, right? And same thing if Cincinnati comes first. There's going to be 6 ways to order the remaining 3 cities. And if Miami comes first, then there are going to be 6 ways to order those 3 cities. And so in total, there's going to be 6 plus 6 plus 6 plus 6, 24. There's going to be 24 ways to order those 4 cities, just those 4. Now, what I want you to notice is that this is just 4 times 6, right? This is just 4 times 6. And 6 was the previous answer. So that kind of makes me think, well, can I describe 6 in terms of its previous answer? So I described 24 in terms of its predecessor, right? It's 4 times 6. Can I describe 6 in terms of its predecessor? Well, yeah, 6 is 3 times 2, right? And can I describe 2 in terms of its predecessor? Yeah. 2 is just 2 times 1. So notice that here we have the predecessor. And here we have the number of things. So if I had to guess 5, I would guess that the number of ways that you could order 5 objects would be the number of things, 5, times the predecessor, 24, right? So 5 times 24. And let's see. That's 120. Okay? Our goal is to figure out how many ways we can put 9 cities in order. So we could continue this process. But here's what I want to here's another thing to point out. So saying that 6 is 3 times 2 is the same thing as saying that 6 is 3 times 2 times 1. And saying that 24 is 4 times 6 is the same thing as saying 4 times 3 times 2 times 1, right? Because 6 is just 3 times 2. 3 times 2 times 1. And this one, similarly, we could say is 5 times 4 times 3 times 2 times 1. Okay? So, if we use some inductive reasoning, we can say, all right, so then if there are 9 things to put in order, right? When there were 2 things to put in order, we said it was 2 times 1. If there were 3 things, we said it was 3 times 2 times 1. If there were 4 things, we said it was 4 times 3 times 2 times 1. And if there were 5 things, we said 5 times 4 times 3 times 2 times 1. So if there are 9 things to put in order, I'm going to guess that it's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you know anything about counting problems, then you know that this has a name. This is called the factorial. So if you know about factorials, then that's awesome. If you don't, that's okay too. So, but this is 9 times 8 times 7 times 6 times 5. Okay, so what do we get? It's 362,880. Okay, now imagine if you hadn't done this inductive reasoning here. Imagine that you had just tried to list off all 362,000 possibilities. You would have been here for days just trying to list off all the different possibilities. It would take you a long, long time to do that. But instead, we can use some inductive reasoning, and we can get to this answer. By the way, there is a deductive way to get this same answer, but we won't go over it right now. Okay, so inductive reasoning is very nice. However, as useful as inductive reasoning is, it can sometimes mislead us into believing things that aren't true. So, for example, let's say that we want to divide a circle into regions by selecting points on its circumference and drawing line segments from each point to each other point. Now let's use inductive reasoning to find the greatest number of regions we would get if we had 6 points on the edge of the circle. So I'm going to go to a tool online called Geogebra to do this problem, but I want to make a little chart. So I want to say number of points and then number of regions. And we'll start with 1 point, but let's go to Geogebra. Okay, and I'm going to go to geometry here. Okay, and I'm going to hand myself a circle. Make it kind of big so that we can split it into a bunch of parts. So the question is, if I have only 1 point on the circle, and I connect it to all of the other points that I've labeled on the circle, how many regions do I get? Well, if I only have 1 point, then I only get 1 region, right? But let's say that I have 2 points. So let's put another point on there, like that one. And then we can join these two. Now, how many regions do I get? Well, I've split the circle into 2 regions, right? So let's go back to my paper here real quick. Right? So if we have 1 point, then we get 1 region. If we have 2 points, then we get 2 regions. What if we have 3 points? So let's add another point, maybe here. And then we have to connect this point to all of the other points. So we're going to connect these two, and we're going to connect these two. Okay? Now how many regions do we get? We've got 1, 2, 3, 4 regions. Okay? So 4 regions this time. So number of points, when we have 3 points, we get 4 regions. Okay, let's do another point. Okay, now I have to connect this to all the others. And then I have to count up the number of regions, and it starts to get a little tricky, but we've got 1, 2, 3, 4, 5, 6, 7, 8 regions now. So 8 regions. So when there are 4 points, there are 8 regions. Okay, let's do one more. One more point. I'll add another point, let's say here. And we've got to connect that to all the other points. So connect it there, 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 and there. And then we have to try to count up the regions. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 regions. Whew. 16 regions. So 5 points, 16 regions. Now what do you notice? It's doubling each time, right? So here you doubled. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And so your guess... So it says use inductive reasoning to find the greatest number of regions we would get if we had 6 points. So our conjecture, 6 points. 6 points would give us, we had 1, 2, 4, 8, 16, so it's doubling each time. So if we had 6 points, if we doubled 16 again, we would get 32. Okay, so that's like the logical conjecture that you would arrive at based on inductive reasoning. Okay, problem is that's not correct. We have to be careful here, so I'll try to show you. But let's say that we added one more point. And now we connect this to all the others. That one, that one, that one, that one, and that one. Okay. Now, let's try to count these up. Holy schmoly. I'm going to try to count all the ones above this line right here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then down here, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I can't remember if I counted that one, so maybe 27 or 28. 29, 30, 31. Okay, 31. The correct answer is 31. You can kind of pause the video and try to count it yourself, but there are 31 regions here, not 32. And we know that, you could try to move these points around to get, well, I didn't want to do that. But you could try to move the points around to get a different number of intersections. But notice that, well, obviously, if these points coincide, you don't really have 6. But you could rearrange the points so that you get an so look at this one right here, right? So notice that here you have 3 lines intersecting at this one node right here. That decreases the number of regions, right? As soon as you move this away, you get an additional region. So we know that the maximum number of regions happens whenever all of your lines only have whenever all of your nodes only have 2 intersections, right? So there's only 2 lines here, 2 there, 2 there, 2 there. And you can check all of the nodes and you'll see that there's only 2 lines intersecting at each node. That's going to give you the maximum number of regions, and when you count them up, you only get 31. So that's kind of interesting. It's very dissatisfying because it seems like the answer should be 32, but in fact it's 31. So the conjecture that you'd get with inductive reasoning is that there should be 32 regions, but actually there are only 31. Okay, so the point I'm trying to make here is that as nice as inductive reasoning is, it can sometimes mislead us into thinking certain things are true that are not actually true. Which is why we try to use deductive proofs. Once we have something that we think is true based on inductive reasoning, we try to prove it deductively, right? To help us avoid making mistakes like this. But anyway, so inductive reasoning is really powerful, really nice, but it has its limitations. It can mislead us sometimes. And if you're interested in seeing some more examples of places where inductive reasoning fails, you can watch this video. I'll include it in the lecture, so you can watch it if you want. Anyway, but this tells us that, okay, so inductive reasoning isn't all there is to math. We've got to be able to prove things deductively, right? So let's practice our deductive reasoning a little bit. So here's a puzzle called a Ken-Ken puzzle. And I'll be honest with you, I had no idea that these things existed before I prepped this particular lecture. But anyway, here we go. It says, consider the grid of numbers below. This is called a Ken-Ken puzzle. You are allowed to fill in all the smaller squares using the numbers 1, 2, 3, and 4. However, no number can be repeated in any row or column. The small numbers in the corners of some cells give instructions as to what must appear in the colored regions. For example, the 2 minus, so the 2 minus here in square D2, so this is square D2, so this little 2 minus means that the numbers you place in this turquoise region, so squares D1 and D2, they have to have a difference of 2. So that's what the 2 minus means. It means that when you subtract the numbers, you should get 2, right? Similarly, the 10 plus in squared d4, so this 10 plus means that when you add this number plus this number plus this number, you have to get 10, right? So let's see if we can complete this puzzle. Okay. So I know that, I'm just picking a place to start, okay? I've never done these kinds of puzzles before. I'm going to use a pencil though, because I'm pretty sure I might have to erase at some point. But I'm just picking a place to start. I'm going to start with this green stuff. I know that these green squares have to add up to be 6. And I know that I can use 1, 2, 3, and 4. If I use 2 and 3, then I'll get 5, and then plus 1 is 6. So I know that I have to use 2 and 3. What I don't know is whether the 2 should go here and the 3 should go there, or if it should be the other way around. Maybe 3 should be here and 2 there. So I'm just going to guess 2 and 3, and if I need to change it, I will. Now remember, you're not allowed to have repeating numbers in any rows or columns, so if I put 2 and 3 here, then 4 has to go there. Okay, and then I also know that these two squares have to add up to be 6. This looks like the same color as this. That was just my printer. This was supposed to be kind of like a purplish color, I think. Anyway, so when I add these two things together, I should get 6. Well, if this is 4, then this has to be 2. And then I've got 2, 3, and 4. That means this has to be 1. And then these two squares have to subtract to give me 2. And since I know this is a 1, that means this has to be a 3. Right? Because 3 minus 1 is 2. Okay. So I guessed right. So the 2 does go here. If I had put the 3 there and the 2 here, I would know that I would have to change it because this one has to be a 3. But I didn't make that mistake. So I guessed correctly. That's a 2. That means a 4 goes there. Oh, which is good news for me because 4 minus 1 is 3. Okay. Oh, and that means a 2 has to go here. Right? And what am I missing here? I'm missing a 4. And let's make sure. 4 plus 4 is 8 plus 2 is 10. So that works. What am I missing in this row? I'm missing a 3. And here I'm missing a 2. And 3 minus 2 is 1. Okay. So there you go. Notice that that was all pure deduction, right? It was all purely deductive. Okay, I was making the moves that I had to make based on the rules that were given to me. So that's deduction. Okay. Here's another deductive type of thing. It says 4 students, Alex, Carmela, Noah, and Winnie, participate in different college activities, debate team, basketball, orchestra, or theater. Use the following clues to determine the activity of each student. Okay. So the clues are, Winnie lives in the same apartment complex as the musician and theater participant. Okay, so we know that Winnie is not the musician or the theater participant. Okay, that's good. Clue 2 says the musician and Noah were friends in high school. So Noah's not the musician. Okay. Clue 3, Carmela has a heavier course load than the basketball player, but fewer credits than the theater participant. Okay. And then Noah, who has the fewest credits, is not on the debate team. Okay. So here's what I'm going to do. I'm going to arrange this into a chart. So I'm going to put the people down this way. So we've got Alex, Carmela, Noah, and Winnie. And then I'm going to put the activities across the top. So the activities were debate team, basketball, orchestra, or theater. Okay, and what I'm going to do is if I can determine that a particular person doesn't do an activity, I'm going to put an X through that box. So and then let's go through this from the beginning and use our deductive reasoning. So it says Winnie Winnie lives in the same apartment complex as the musician and theater. So Winnie is not in orchestra. She's not the musician, so she's not in orchestra, and she's not in theater. We know that because the clue tells us that she lives in the same apartment complex as those two people, so she's not those two people. Okay. Then it says the musician and Noah were friends in high school. So Noah is not the musician. Maybe I should have put M instead of O. So I'll say M, right? Musician. Okay. Third clue says Carmela has a heavier course load than the basketball player, but fewer credits than the theater participant. So she has a heavier course load than the basketball player. That means Carmela is not the basketball player. Fewer credits than the theater participant, so she's not in theater. Okay. And then clue 4 says, Noah, who has the fewest credits, is not on the debate team. So we know that Noah, so earlier we knew that Noah was not the musician. Now we also know that Noah is not on the debate team. Okay, but what else do we know? We know that Noah has the fewest credits. And we're told in clue 3 that Carmela has a heavier course load than the basketball player, but fewer credits than the theater participant. So if Noah has the fewest credits, then Noah is definitely not the theater participant, because the theater participant has more credits than Carmela does. And Noah has the least number of credits, so he can't be the theater participant. Okay, so there we go. I put this in the wrong place. Noah didn't do debate. So, right, it said Noah's, step 4 said Noah's not on the debate team. So I should have put the X through this D for debate. Because Noah is the basketball player, right? He's the basketball player. Okay. Can we figure out anything else? Well, Winnie can't be the basketball player because Noah is. And we know that all 4 students do different activities. So she can't be the basketball player. That means Winnie must be on the debate team. Okay? If Winnie's on the debate team, then Carmela can't be on the debate team, which means that Carmela must be the musician. And then finally, Winnie's on the debate team, so Alex isn't. Noah's on the basketball team, so Alex isn't. Carmela's in orchestra, so Alex isn't. That means Alex must be the one in theater. And there you go. Right, so Alex is in theater. So Alex is in theater. Carmela is in orchestra. Noah is in basketball. And Winnie is on the debate team. Okay? And that's that, right? So deduction. Okay. So you have used deduction in the past, maybe not in the form of like a formal proof like what we did here on page 1, but you've used deduction before, and it's a very useful mathematical tool. Now, coming up with deductive proofs of conjectures often requires a lot of creativity and effort, and in fact, there are lots of things in math that we suspect are true, so we have lots of conjectures that we haven't been able to prove yet. So to finish up our discussion of inductive and deductive reasoning, we're going to look at a very famous conjecture called the Goldbach Conjecture. If you're able, so this conjecture hasn't been proven. If you're able to prove it, then great fame and fortune awaits you for sure. But anyway, so here's the Goldbach Conjecture. It says, in 1742, Christian Goldbach made the conjecture that we could write every even integer greater than 2 as the sum of 2 prime numbers. Okay, a prime number is a number that can be divided evenly only by itself and 1. So if you start thinking about what the prime numbers are, the first one would be 2, right? 2 is divisible only by itself, 2, and by 1. Same thing with 3. 4, on the other hand, 4 is divisible by itself and 1, but it's also divisible by 2. So 4 is not prime. Okay, 5 is prime, 6 is not prime, 7 is prime, 8, 9, and 10 are not prime. 8 can be divisible by 4, 9 is divisible by 3, 10 is divisible by 5, right? But 11 is prime, 13 is prime, 17, 19, 23, 29. And then they start to get further and further spaced out, okay? But anyway, so Goldbach's conjecture is that we can rewrite any even integer as the sum of two prime numbers. So let's illustrate this conjecture by expressing the even integers 20, 48, and 100 as the sum of two prime numbers. Okay. So 20 we could rewrite, for example, as 10 plus 10, but that wouldn't do the trick because 10 is not prime. We want to find two prime numbers that add up to be 20. We could try 11 and 9. 11 is prime, but 9 isn't. So 11 and 9 won't work. We could try, well, 12 won't work. We could try 13. 13 and 7? 13 and 7, they're both prime. Okay, so sure enough, 20 can be rewritten as the sum of two prime numbers. What about 48? 48. 48, well, we could try 24 plus 24, but 24 is not prime. So maybe we could try 23. It would have to be 23 plus 25. But 25 is not prime. Okay. We could try 22 won't work. 21 won't work. 19, we could try 19. So let's see. 48 minus 19 is 29. Yeah, so 19 plus 29, that adds up to be 48. Okay, so sure enough, 48 can be rewritten as the sum of two prime numbers. What about 100? I'm going to try from the opposite end of the spectrum, so maybe we could try 99 and 1. Well, 99 is not prime, and 1 doesn't really count. What about 98 and 2? Well, 98 is not prime. 98 is divisible by 2, so that won't work. What about 97 and 3? 3 is prime. Is 97 prime? Well, you could try it on your calculator. You could try, well, what's 97 divided by 2? Not divisible. 97 divided by 3? Not divisible, right? 97 divided by 5, not divisible. And you could go up and see if it's divisible by any of these numbers. I'll tell you right now that it's not. So 100 could be 97 plus 3. Both prime numbers. That's not the only way to do it. I think you could do like... I'd have to think of another example. But there's multiple ways to rewrite these numbers as the sum of two prime numbers. But anyway... So those three seem to work. So it seems like this is a true statement. In fact, most mathematicians believe that this is true, that every even integer greater than 2 can be rewritten as the sum of two prime numbers. But it hasn't been proven yet. Now, one question to kind of think about is, why only the even numbers? Why can you not write the odd numbers as the sum of two prime numbers? And one thing that you might notice is that most of the prime numbers are odd. 2 is the only exception, right? So, and then we know from what we did on page 1 that the sum of two odd numbers is always going to be an even number. So that if you add two prime numbers, chances are it's going to be even, right? So that's why only the even numbers are included in the conjecture. But anyway, for your information, Goldbach's conjecture hasn't been proven for all even numbers, but it has been verified for all even numbers less than 4 times 10 to the 18th power. That's a 4 with 18 zeros behind it, so it's a huge number. So we know that this conjecture is true for all numbers less than this. We just haven't been able to prove it for every number. Again, if you can do it, if you can do it, Fame and fortune await you. Okay, that's it for this lecture.